So good evening, everyone. Today I am going to take this tutorial, Week 6 tutorial. So for this NPTEL course, named as a study guide in organic retrosynthesis problem solving approach. The course instructor of this course is Professor Samik Nanda from IIT Kharagpur, and I am Anirban Maiti. So I am one of the TA for this course. So coming to the our topic of discussions. So previous tutorials also I have told about that synthetic equivalents and syntones. So whenever uh, we are going to disconnect a CC bond, that time we we could get this donor syntone and acceptor syntone, right? So donor syntone basically it means ki it will donate electrons, and acceptor syntone means it will accept the electrons. Okay, so this will happen when you will do the CC1 disconnection via heterolytic cleavage, right? And in case of homolytic cleavage, homolytic cleavage you will get two radicals, right? Because this bonding electron, so this bond is having two electrons. So after homolytic cleavage, each carbon will take one electron, so it will give two radicals, right? But in case of heterolytic cleavage, it will give one carbanion and one carbocation. So this carbanion is donor syntone and this is acceptor syntone, right? Yeah. So I have shown many examples of donor syntones and how we can get the synthetic equivalent for the donor syntones and acceptor syntones. Also, uh, I have written here, so you can see the synthetic equivalents also, right? So you can see the corresponding synthetic equivalents for each acceptor syntone, right? So, so so this is our today's example for retrosynthetic analysis. So if you think this molecule, if 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 this molecule is given to you, so and you want to do the retrosynthetic analysis for this molecule, how we can think about. So if you see this molecule, it is having an um, olefin, right? So terminal olefin, and the terminal carbon contains two deuterium, right? So instead of hydrogen, it contains deuterium, right? So how we can think about, so we can olefin, it we can easily prepare from or synthesize from a aldehyde or ketone via Wittig reaction, right? So we can plan a Wittig reaction via this CC1 disconnection approach. Okay, so this aldehyde and this corresponding Wittig salt we have to take. So if you, so that means this aldehyde, how we can get again? So this aldehyde again we can get from the from this olefin, right? So this olefin we can get. So how we can get? So we'll see in forward direction. Basically, this we need here aldehyde, right? So this CH2 CH. Okay. So this is the CH2 carbon, and we need to convert this carbon to aldehyde, right? So we have to oxidize this carbon center to get the aldehyde, right? So how we can? So in forward synthesis, we will see. So what are the functional group interconversions for this retrosynthetic plant? So basically one carbon homologation. So if you see the carbon chain, so this is 1 2 3, and in starting metal you have on two carbon chains. So one carbon homologation of a terminal double bond to a terminally deuterated compound. Okay, deuterated compound. So forward synthesis, let's see. So if you see this forward synthesis, first we have this olefin or alkene, and then we have to do hydroboration oxidation, right? So this is BH3THF. So this reagent we have to use boron, and then so what will happen? So H will come here and BH2 will come here. Okay, so here terminal carbon boron will attach. Okay, then so we have to do oxidation by using NaOH and H2O2. So what will happen? We will get aldehyde at this terminal carbon, sorry, alcohol we add this terminal carbon, right? So first hydroboration, then oxidation. Okay, then we need to convert this alcohol. So this is the primary alcohol, right? So primary alcohol oxidation we have to do by using pyridinium chlorochromate at DCC. Okay, sorry, TCM, dichloromethane, as a solvent. So PCC, what will do, it will oxidize this primary alcohol to its corresponding aldehyde, and we need the terminal olefin, right? So we have to, already we told about Wittig reaction to carry out at the last stage. So we have to perform this Wittig reaction with this special Wittig sol. Okay, so it is having deuterium itself in the Wittig sol. Okay, so basically Wittig reagent, this Wittig reagent will give the corresponding Wittig product. Okay, so this is our target molecule, right? This is our target molecule now, and this is our starting material. Okay, so in three step you can convert this starting material to desired target molecule, right? So now the question is how we can prepare this Wittig sol. Okay, so sometimes this Wittig sol is available, but when it is not available to you, how you can prepare in lab from the easily available starting material. Okay, so basically if you see this Wittig salt, so this is not Wittig salt, this is elide, right? So this is elide. So we have to generate the corresponding Wittig elide from the corresponding salt, right? So this is the elide. So elide we can generate from the corresponding salt. So basically elide mean this is PPH3 plus and CD2 minus. So salt should be CD3 or CD2H. Okay, and corresponding anion, right? So how we can prepare? So basically we can take this trideutyrated trideutyrated iodomethane, right? Trideutyrated iodomethane, and if we carry out the SN2 reaction with PPH3. Okay, so the PPH3 is having lone pair, so it will undergo SN2 reaction. So iodine elimination, leaving group iodine will leave, and it will give this Wittig sol, right? And so this is the sol PPHC plus CD3, and this is the counter anion. Now we have to generate this elide, right? So elide, how we can generate? So basically if we treat this salt with base, we can easily take this proton. Oh, sorry, here it is deuterium. So instead of proton hydrogen we are using deuterium, right? So if we treat with base like in between lithium or potassium tertiary butoxide, strong base, that time we can generate. So you can take this deuterium from this carbon, and it can generate this CD2 minus PPC plus. So this is the elide. Okay, so this is the, as we take elide, we can easily generate. Okay, so this is the first today's first retrosynthetic analysis and forward synthesis. Now coming to the next one. So this is this molecule. If you see, so this is this molecule. Name of this molecule is saccharin. Okay, saccharin. I guess all of you heard about saccharin. So it is an sweetener. Okay, so in many food industry, so they use saccharin as a alternative of sugar. Okay, like carbohydrate sugar. Okay, so it is an alternative of carbohydrates. Okay, so for sweetening your food, so it is an sweetener. So how you can prepare in lab. So first, for preparation or for synthesis of saccharin, you need to do the retrosynthetic analysis. How you can think about retrosynthetic analysis? So this molecule, if you see what it has, okay, so basically it is having this amide here, sulfonamide. Okay, so we can think about this is cn, this cn and this sn bond disconnection approach. Okay, so in NC and in S. Okay, so these two disconnection approach we can think. So basically, this is the disconnection approach so if you treat this molecule with ammonia, we can get this saccharin, right? So now after this disconnection approach, we get this molecule. Okay, so now how we can get this molecule? So basically, functional group interconversion. So methyl here, so methyl mean if we do oxidation of this methyl, so oxidation we have to do. Okay, so functional group interconversion. So for this step, it is oxidation, right? So oxidation we can write like this. So oxidation we have to carry out. So add this methyl. Okay, so this is benzylic oxidation we can say. So we can easily do by using KMNO4 chromium trioxide, right? So now this how we can get. So we can think about electrophilic substitution. Okay, we can think about this CS bond disconnection approach and electrophilic substitution. So what we will have? So this toluene. Okay, so this is called toluene. So if you do the electrophilic substitution of toluene, we can get the corresponding product. So in forward synthesis, we have to carry out from toluene. So we have to start from toluene. So basically, if we do, if we treat chlorosulfonic acid, so this is called chlorosulfonic acid. So this is an acid, and if we treat this acid with toluene, we can get these two products. Okay, so basically this is ortho. This methyl is, so methyl is R group, right? So it is having plus I effect, so it can have this ortho selectivity in electrophilic substitution, this ortho prime and or para directing group. Okay, so this methyl is ortho directing group or para directing group. So similarly we will get these two products. This is ortho product, so this is ortho, and the next one is para, right? So this is the para product. So now in this forward synthesis, one question will arise in your mind. So the question is, so if you draw this molecule, okay, SO2, so this is the SO2. If we draw, this is SO2 OH and Cl, right? So now, so electrophilic substitution, if we think for this toluene, and this is the electrophile, so now we can you can say that this chlorine will leave, okay, in this electrophilic substitution. But instead of chlorine, here what is leaving? This alcohol is leaving. If you see the product, chlorine is there, okay, in your product. So basically this oh is living in this case. So how it's happening? But chlorine is better living group. Now the question is, then how this alcohol is living here instead of chlorine? So question is, the question, if you think, so if you have to think about this reagent. Okay, this is chlorosulfonic acid, this is an acid. So acid what will generate? So acid generally it will generate H plus. Okay, so it will dissociates H plus ion. So this H plus ion what will happen? So this alcohol, so it will catch this H plus and it will make it OH2 plus. Okay, this OH2 plus. So now in the system, this OH2 plus is better leaving group in compared to chlorine. So what will happen in electrophilic substitution? So and then it will fall back and this OH2 plus will leave. Okay. So now you got clear idea, okay, why this chlorine is not leaving, whereas this alcohol is leaving. Okay, so now see, you got both ortho and para product. S- So we have to carry out with this ortho product. Okay, so if you see this saccharin molecule, so it is having this ortho substitution. Okay, so we have to, in forward synthesis, we have to start from this ortho product and do move to the next reaction. Okay, so my next reaction is that is chlorine we have to substitute with ammonia. Okay, so basically this substitution reaction, so again it will attack to sulfur and chlorine will leave. Okay, okay, so you will get this sulfonamide. Okay, now this methyl what we have to do, so this is benzylic position. Okay, so benzylic position we can easily do the oxidation at benzylic position by using uh, what reagents. Okay, by using we can use a KMNO4 or chromium dioxide for benzylic oxidation. So like that we have to use this KMNO4 to oxidize this methyl, that toluene methyl, to get this carboxylic acid. Okay, now what is the next, we have to connect this CN bond, right? This CN bond we have to connect. So how we can, if we heat this compound, so it will cyclize. Okay, heat this compound, it will cyclize with the elimination of water. Okay, so water will eliminate in after heating, so and we will get the cyclized product, that is saccharin. Okay, so our target molecule we could get easily from this toluene. Okay, so how you can see how easily we can synthesize saccharin in from toluene in lab. Okay, so these are interesting example. So now coming to the next example. Okay, so next example is again from this again with this aromatic ring. Okay, so how we can plan about this retrosynthetic analysis. So if you see this molecule, so if you see the functional groups, what it contains. Okay, so basically in benzene aromatic ring, it is having chlorine, OMe, and here it is O substituted alkyl group. So this oxygen is substituted with alkyl group. So we can think, and this if you see, this is ketone and this is ketone. And if you see the relation between these two ketones, so this is 1, 2, and 3. Okay, 1 3 diketone compound. Okay, so 1 3 diketone compounds mean this carbon is this proton, yeah, this number 2 carbon is highly acidic. So we can easily think about this CC1 disconnection, because this enolate we can easily generate. Okay, so this is the CC1 disconnection. And if you see this here, we can think about this CO bond disconnection. Okay, so because this alcohol is electronegative and this is electropositive. Okay, delta positive, we can think about here also at this carbon delta positive. Bec- and this O minus you can easily generate, and here this C minus enolate you can easily generate. Okay, so first retrosynthetic plan, we can think about this CC1 disconnection, and we can get the corresponding acceptor syntones and donor syntone, right? So this is the acceptor syntone and this is the donor syntone. Now what will be the corresponding synthetic equivalent for these syntones? So synthetic equivalent is normal. So this will be the corresponding synthetic equivalent. So 1,3-diketone, uh, and this will for this is the CBr. Okay, because you can easily do electrophilic. You can easily do this substitution reaction with this enolate, Now this synthetic equivalent, how we can get? So we can, you can think about this CO bond disconnection. Okay, CO bond disconnection again. So this will be delta negative, and this carbon will be delta positive. Okay, so we'll get this corresponding synthetic equivalence for this disconnection approach, right? So now coming to this forward synthesis. Okay, so forward synthesis we have to start from this aromatic ring, right? And this bromo to dibromo derivative. Okay, 1,6 dibromohexane. Okay, so first we have to take this compound aromatic phenol. Okay, phenol derivative. So this is the phenol derivative. And if you think about pK of this phenol, I have written here pK of this phenol is 10. Okay, so we have to do the substitution reaction. So we need one base. So K2CO3 is using as a base. So the pK value of this corresponding uh, conjugate acid of this base is 10.25, and this electrophile we are using, okay, 1,6 dibromohexane. Okay, now what will happen? So first K2CO3 will take this proton. Okay, right? So K2CO3 will take this proton, and this alcohol will attack to this carbon. So this SN2 reaction, okay, and you will get a corresponding product, right? So now we have to do the some Finkelstein reaction. Okay, we have to convert this CBr carbon bromine to C iodide. Okay, by using sodium iodide and in acetone. Acetone is the solvent. Okay, so Finkelstein reaction. If you do, what will happen? We will get this corresponding iodo compound. Now what's the next? Next is if you see, we have to generate another enolate, right? So enolate from one tree corresponding one tree diketone we have to generate. Then again substitution reaction. So this is the enolate, right? So in this slide we got this compound where we are having this C iodine bond. Okay, so now we have to do electrophilic substitution with this compound. So for that nucleophile we need. So which nucleophile we will use? So this nucleophile. So basically we have to make this 1,3 diketone to corresponding enolate by using base. Okay, so which base we can use? So pK of this 1,3 diketone compound. So the acidity of this proton is 9. Okay, the pK value for this proton is 9. So now the K2CO3 is already we have shown the corresponding pK value of this of its conjugate acid is 10.25, right? So it will abstract this proton, and it will generate the corresponding enolate, and that enolate will attack to this Ci bond. So it will act as a electrophile to give this compound. Okay, so this enolate will generate. So which enolate basically? So this enolate will generate. So this enolate will react. Okay, now so you will get this corresponding compound. Okay, so this mechanism, I guess, sorry, but forward synthesis, guess you got an idea how we can synthesize this molecule from the corresponding phenol derivative. Okay, very simple transformation it contains. Okay, so the next example, so this is an interesting example. So this molecule, how we can synthesize from this? Okay, so if you see this target molecule, so target molecule it is having one benzyl ether. Okay, so the left side of this target molecule contains this benzyl ether. Okay, so this is the benzyl ether, and the right side it contains carboxylic acid side chain, and the middle carbon. So middle carbon, if you see, it is chiral, and the stereochemistry, if you say, this is S, right? So this is the S stereochemistry. Okay, if you do the IUPAC nomenclature, RS nomenclature, you'll get S. And the starting material already written here. And if you see the middle carbon stereochemistry is R, right? So that means we have to convert this to S to R. Okay. So if you see this target molecule, it is having this benzyl ether side chain at the left side, and right side it is having carboxylic acid chain, and middle carbon is chiral. Okay, and the chiral, if you do the RS nomenclature, it is S. Okay, now in starting material, if you see the chiral carbon, the stereochemistry of this center is become R now. Okay, and the left side it contains carboxylic acid, and right side contains the alcohol, right? So now, which molecule, how we can synthesize this target molecule from starting material? Basically, we have to how the functional group interconversion. If you see, what are the functional group interconversions we have to do? So basically, this carboxylic acid we have to convert to benzyl ether, and primary alcohol. This primary alcohol we have to convert to carboxylic acid. Okay, so in forward synthesis, okay, so this is the target molecule, right? So this is the target molecule, and this is the starting material. Okay, so for this we have to convert to corresponding carboxylic acid. Okay, so what we have to do, we have to first, we can do the protection of this alcohol. Okay, so this alcohol protection we can do by using dihydropyran. Okay, so this is the dihydropyran. Okay, so this is the pyran. If it is having double bond this side, that is called pyran, and so it is only one double bond it is having, so it is called dihydropyran. Okay, so in a catalytic H plus, okay, what will happen? So this will catch H plus. Okay, H plus. So this lone pair will help. So and it will catch this H plus. Okay, so basically oxonium ion will form. Okay, oxonium ion will form to this carbon oxygen bond, and this alcohol will add to this carbon of this oxonium ion. Okay, so oxonium ion I did not draw the intermediate, so basically it will go to oxonium ion. So after the protection of this alcohol with dihydropyran, what we will get? We will get the tetrahydro. It is become now tetrahydropyran. Okay, so this is tetrahydropyranyl protection of this alcohol. So this we can write as THP. Okay, so this protecting group we can, in brief, we can write as a THP. Okay, so now what we have to do? This carboxylic acid we have to do reduction. Okay, to get CH2OH. Okay, this alcohol, corresponding alcohol, if we want primary alcohol, then we have to do the acid reduction with LAH, and then this OR cup with sodium hydroxide and water. So we'll get this alcohol and this side OTHP, right? So this we will get. So basically, then what we have to do the next? So next we have to do benzylation at this alcohol. Okay, so benzylation, what for benzylation? So this is benzyl bromide we have to use as a electrophile, and then sodium hydride as a base, and DMF. DMF is solvent. Okay, so for if you use sodium hydride as a base, okay, so the better solvents are for sodium hydride is DMSO or DMF, because what will happen that DMF and DMSO, it will coordinate that sodium of sodium hydride. Okay, so this base become more free and it can you easily abstract proton. Okay, so sodium hydride is will show better, uh, it will have better effect in DMF and DMS. Okay, so for benzylation we will use sodium hydride in benzyl and benzyl bromide in DMF, and we will get the protection benzyl protected alcohol. So this is the benzyl ether, right? So now we have to do the protection of this tetrahydropyranyl group. Okay, OTHP. So how you can do, if we treat with HCl, dilute HCl, so mineral acid H3O plus, then we can easily get the alcohol. Okay, deprotected alcohol. Okay, THP deprotected alcohol, primary alcohol. So this is a primary alcohol, and if you see this target molecule, so it is having carboxylic acid at the right. Okay, so this primary alcohol to acid oxidation we have to do by using Jones oxidation condition. Okay, so this is how we can get the corresponding target molecule. The next slide, next example. So this example, so this the target molecule, and what are the characteristics of this target molecule. Okay, so this target molecule is an lactone. Okay, ester, cyclic ester. So cyclic ester mean lactone, and how many member lactone? So this is 5 member lactone. So basically it is alpha, beta. So this is beta carbon and this is gamma carbon. Okay, so this is a gamma lactone with having beta substitution. Okay, so beta substituent, that is allyl group. Okay, so this allyl group is present at beta position of this gamma lactone. So basically how we can get, so we already have the starting material. So starting material it is this. Okay, so this, if you see the starting material and target molecule, so what are the difference in target molecule and starting material? So this side chain, allyl side chain is same. Okay, and the stereochemistry, if you see, both are beta stereochemistry. Now the question is that what are the other changes in target molecule? So if you see here in starting material, the bottom side carbonyl group is there. Okay, so this ester carbonyl is lactone carbonyl group is bottom side, but in target molecule it is up side. Okay, and upside in starting material, this CH2O THP group is there. Okay, so OTHP already we discussed in last slide, that is the protecting group for alcohol, and the protecting group is tetrahydropyranyl. Okay, tetrahydropyran. So we can get from dihydropyran, right? So basically, if you see the target molecule, so we have to remove this, and this carbonyl group we have to install at this carbon, right? So how we can do, interesting, right? Yeah, so this molecule, if you see, so if we do LH reduction, so LH is lithium aluminum hydride, so hydride based reducing agent. And if you see your molecule, your starting material, it is having this lactone. Okay, so lactone ester. Okay, so LH reduction, what will happen? Reduction of this lactone will happen. So basically, you will get this alcohol, and this CH2O is primary alcohol. So this secondary alcohol and this primary alcohol, right? So this we will get. Now the next step, already condition is written. H3O plus. Okay, tetrahydropyran. So what will happen? So tetrahydropyran, what will do? It is basically deprotect. Okay, so in H3O plus mineral acid treatment, it will deprotect and it will give the corresponding primary alcohol. Okay, so this primary alcohol it is having, then secondary alcohol, and again we are doing the deprotection of this primary alcohol to get the alcohol. So it will become triol. Okay, so this compound is triol. So these triol compounds are highly polar, right? So this, after getting this compound, the next target is we have to do NaIO for cleavage. Okay, NaIO for cleavage. So basically NaIO for will cleave 1,2 diol. So this we are having this 1,2 diol. So NaIO for cleavage of this 1,2 diol will give the corresponding aldehyde, right? So this mechanism I am not discussing. So I guess all of you know. And NaIO for cleavage, the oxidate, this is called oxidative cleavage. So we will get the corresponding aldehyde, right? So this aldehyde will get, we will get. Now the now whenever you will get whenever you will perform this diol cleavage, so this aldehyde will generate. But what will happen, this alcohol is having, and if you see, this is one carbon, number one, this is two, three, four, five. So it can like cyclize to this aldehyde, and it will form hemiacetal. Okay, hemiacetal. So whatever, whenever this type of case is there, mean this alcohol at 5 position and aldehyde at 1 position, that time this hemiacetal will form. Okay, so this will be in equilibrium with this hemiacetal. So so this, after Na for cleavage, you will directly get this hemiacetal. Okay, so in your target material, we are having this ketone here. Okay, so this carbonyl CO group here. So we have to do oxidation of this hemiacetal to get the corresponding lactone. Okay, so we can do Jones oxidation, right? So Jones oxidation we can perform, and we can get the corresponding lactone. So 5 member gamma lactone. So this is our target molecule, and this is our starting molecule. Right. So just a minute. Just a minute. Okay, so in this example, basically it is having this for this retrosynthetic analysis. So this molecule it contains, so this is alpha beta gamma lactone. And if you see the side chain, so side chain it is having allyl group at beta position, right? Just a minute. Yeah. So this molecule, so if you see this is alpha, beta, and gamma. Okay, gamma lactone. So now, so this gamma lactone, what it will do? So we can easily so the starting material also it is given here. Okay, so here starting material also given, and this is the target molecule. Okay, TM. So now if you see the differences between the target molecule and starting material, so if you see this side chain is common for both molecule. Now the difference is the in the starting material here bottom side is lactone, okay, and in target molecule upside is lactone. And if you see the target molecule, so this group is vanished, okay, so this group is vanished. So how we can plan, how we can do the corresponding retrosynthetic analysis for this molecule? So we can do okay, let's go to the forward synthesis. So this is a forward synthesis. So forward synthesis, what we have to do fast? So basically, we can do some reduction of this lactone. So reduction of this lactone, so it will give this LH reduction. LH reduction, what we will get? So we will get the corresponding alcohol. Okay, two alcohols we will get. So this is the secondary alcohol. So it will give this secondary alcohol at this carbon and primary alcohol at this carbon, right? So basically, first LH reduction to get the diol. Okay, so now this is diol we got now. So the next is tetrahydropuran. So tetrahydropiran, already last slide we have, last to last example we have discussed about this tetrahydropiran protecting group. So tetrahydropiran is basically this is O, right? So this is the RO. Okay, so this is RO. So this is RO, and this is the tetrahydropiran cysteine. So this is THP, right? So this is THP. Now this THP production we can do by treating with H3O plus. Okay, so basically this will catch OH. Okay, this alcohol will catch OH H plus, and then this oxonium ion will form. So basically this will fall here, and this RO bond will break. Okay, and we will get the corresponding alcohol. So H3O plus, after treatment with this H3O plus, we will get the corresponding triol. Okay, so this triol we will get. Now how we can protect this alcohol as a THP group? So if we are having um, R alcohol with dihydropyran, right? So what is dihydropyran? So dihydropyran is this. So this is the dihydropyran. Okay. So now if you treat this dihydropyran with H plus, what will happen? So this oxygen lone pair will fall, and this CC double bond will catch H plus. Okay. So it will catch the acidic proton. So it will generate basically this oxonium ion. Okay. So basically it will generate the corresponding oxonium ion. Okay. This oxonium ion it will generate. So this oxonium ion are electrophilic now, right? So what will happen? This alcohol will act as a nucleophile, and it will add to the oxonium carbon, and it will give this tetrahydropyran. Already I drawn the structure of this tetrahydropyran, and you can see. Okay, so now after this protection of this THP group, we can easily do the deprotection by using treating with H3O plus mineral acid. So to get this triol, now this NaIO4 cleavage, so in not NaIO4 cleavage, so this is the 1 to diol cleavage. So this is 1 and this is 2. Okay, so this is 1 2 diol we are having in this system. So basically we can do oxidative cleavage by using NaIO4 as a oxidizing agent. So we can get this corresponding aldehyde. Okay, so this aldehyde we can get. Now this aldehyde, if you see the relation between this primary alcohol and aldehyde, so this is 1 2 3, so 4 carbon. So fourth carbon is having primary alcohol. Okay, so this primary alcohol may attack to this aldehyde carbon. So it will attack to the aldehyde carbon, it will form the hemiacetal. Okay, so this is called hemiacetal, and this hemiacetal actually it will, this aldehyde will exist as a hemiacetal form after the NaIO4 mediated diol cleavage. Okay, so after this hemiacetal formation, what is our next target? So our next target is to carry out the oxidation of this carbon. Okay, so this hemiacetal to get the corresponding lactone, and we can treat with Jones oxidation condition, chromium trioxide H2O, H2SO4 acetone. So that Jones oxidation condition, if we do, then we can get this alcohol oxidation, so lactol oxidation to get this corresponding lactone. Okay, lactol to lactone. So this is our starting molecule, and target molecule also we got now after how many step? One, two, three, four step. Okay, so after four step we got this starting material to target molecule. Right. So now the next problem, next retrosynthetic analysis. So this molecule is known as trans 3 dihydroxy pipecolic acid. Okay, so how we can plan for retrosynthetic analysis for this molecule? So this is, if you see this molecule, so it is having this six member piperidine ring, six member piperidine ring, and having the trans geometry of this alcohol and acid. Okay, so this alcohol is alpha and carboxylic acid is beta, and the name is, it is written here plus this, so this is plus isomer trans 3 hydroxy pipecolic acid. So retrosynthetic analysis, so this we can plan from this molecule. Okay, so this molecule basically, so this alcohol we can protect OPG1 protecting group 1, and this alcohol, so this is now CH2 alcohol, so CH2OH, right, protected alcohol, OPG2 protecting group 2. So PG mean protecting group. Okay, so now this protecting group, we already, okay, this CH2OPG, so CH2OH we can do oxidation of this primary alcohol, we can get this acid. Okay, and if we deprotect this alcohol, then we can get this as alcohol. Okay, so this is the functional group interconversion for this step. Then the next step is, so basically this cn bond formation, cn bond disconnection approach. Okay, so this cn bond disconnection approach we can think, and so then, so this will be x. Okay, this will be x and this will be amine, corresponding amine. So basically SN2 reaction will give this piperidine ring. Okay, six member piperidine ring. Now this amine how we could get? So basically this amine we could get from this protected alcohol. Okay, so basically this OPG3 mean different protecting group. So we can do this alcohol to leaving group. Okay, this alcohol we can convert to leaving group, and then this cyclization substitution reaction we can carry out easily. So now this compound is protected alcohol, triol, protected triol, and this amine derivative, how we could get this amine from this alcohol. So this is now tetraol, okay. And this tetraol, how we could get? So basically we could get from this olefin, okay. So this olefin, if we do diol formation, okay, osmium tetroxide mediated diol formation, we can get this diol, another two diol, okay. And this olefin we could get from Wittig reaction, right? So Wittig reaction from corresponding aldehyde and the corresponding Wittig ylide, we can get this aldehyde, right? So it is simple. So coming to forward synthesis, yeah, forward synthesis, we'll start from this 1 3 diol, sorry, 1 2 3 4 1 4 diol, be it 1 4 butane diol. So if you treat this 1 4 butane diol with one equivalent of sodium hydride and one equivalent of PMB chloride, paramethoxybenzyl chloride. So this is the, so basically we want to protect one alcohol, okay, okay, one of the alcohol. So by using one equivalent of the reagents, okay, so we can easily protect one of the alcohol as a PMB, and then another free alcohol we can do the oxidation by using PCC, okay, in DCM. So basically this alcohol we have protected here as a OPMB, and this alcohol, right side alcohol, we are oxidizing to get this aldehyde. Now we have to do, as we have seen, this Wittig ylide I have drawn here, and this in DCM reflux condition, it will give the corresponding Wittig product. Okay, the Wittig product means this carbon and this carbon will form bond, CC double bond, right? So CC double bond it will form, and we will get the corresponding alpha beta unsaturated ester, okay. So this conjugate ester we will get. So now we have to do dival H reduction, okay, dival H reduction of this ester to get the corresponding alcohol, right? So this is the allylic alcohol we can get from this alpha beta unsaturated ester if we do dival H reduction. Now, if you see here, I have mentioned this in workup, we have to use Rochelle salt. Okay, so Rochelle salt when we have to use. So whenever we are doing any dival H mediated reduction in your lab, that time after the reaction you have to use Rochelle salt to do the better workup. Okay, I I told you for better workup you have to use Rochelle salt, because whenever you will perform the Rochelle dival H mediated reductions, that time after the reaction it will form solid. Okay, so it will form solid emulsion. Okay, so dival H mean diisobutyl aluminium hydride, right? So aluminium. So after the reduction it will form some emulsion, solid emulsion. Okay, and if you want to do separation by using separating funnel, basically workup if you want to do, that time you will get difficulty to separate your organic layer from aqueous layer. So because of that solid emulsions, okay, so that's why you have to break that emulsion. So how you can break emulsion? So that Rochelle salt you have to use. Rochelle salt basically it is sodium potassium salt of tartarate, okay, sodium potassium tartarate. So it is an sodium potassium salt, and this Rochelle salt will break, aqueous solution of Rochelle salt will break that emulsion, okay, and it will give clear solution, and you can easily do workup, and you can easily separate your organic layer from the reaction mixture. So this is why we have to use Rochelle salt in dival H reductions while doing workup. Okay, okay. Anyway, so after this reaction, we will get this allylic alcohol. Then we have to do, so this AD mix alpha. Okay, surplus. So this is the surplus condition for dihydroxylation. So surplus got Nobel Prize, very surplus, but not for this asymmetric hydroxylation or asymmetric epoxidation. So he got Nobel Prize for different work. So this surplex epoxy dihydroxylation, 1 to dihydroxylation, asymmetric dihydroxylation we have to perform by using this eddy-mix alpha condition, and we will get this diol. Okay, so basically this is triol now with 92% enantiomeric excess. So what is the next? Next is we have to protect this 1,3-diol with this phenyl orthoformate. Okay, so we have to use this phenyl orthoformate and paratoluene sulfonic acid in DCM. So we will get this 1,3-diol protected compound, and this secondary alcohol is now free. Now we can convert this secondary alcohol we can to living group, right? So we can convert that secondary alcohol to living group by treating with methyl chloride. So OMS will form, right? So here OMS will form, and then next substitution reaction with sodium azide. So sodium azide mediated substitution at this carbon, OMS will leave and we will get this azide compound. Okay, so what is the next? Next is we have to deprotect this OPMB group. So PMB mean 4-methoxybenzyl group, right? So it is another type of benzyl group, but 4 position is having O-methoxy. Okay, so we can easily deprotect by using DDQ in DCM, and we can get this primary alcohol, right? So after getting this primary alcohol, again we have to make this primary alcohol as a leaving group. So we will get this O missile. So then we have to do reduction of this azide to get amine. So H2PDC reduction to get amine. So we will easily in situ we will get amine, right? NH2, and that amine in situ it will react. In situ it will cyclize in by substitution reaction to get to give this 6-member piperidine ring. Okay, so whenever you will get this NH2 and this OMS, so in proper appropriate position, so you will get this 6-member ring here in situ. Okay, so after that we have to protect this uh, N nitrogen as a Bock. So by treating with Bock anhydride in tertiary butanol water as a solvent, we can get this N Bock protected amine. Okay, so next is we have to protect this primary alcohol as a OTBDPS with the help of imidazole as a base in DCM solvent. So we will get this primary alcohol protected compound, and then the secondary alcohol is free now. The secondary alcohol again we will protect with MOM group. So MOM group protection of secondary alcohol using diisopropyl ethylamine as a base, so we'll get this mom protected compound. So this compound is now protected in protection with Bock. Primary is protected with TBDPS, and secondary is with mom. What is the next? We have to deprotect TBDPS. So we can deprotect TBDPS by using any fluorinated fluorine based reagents like fluoride ion based reagent. More so HF is hydrogen fluoride dot pyridine this complex. So this will generate fluoride ion basically, and we'll get this fluoride ion will attack to the silicon of that TBDPS group, and it will break oxygen silicon bond, and we will get this free alcohol. Okay, so after getting this compound, what we have to do? We have to do oxidation of this primary alcohol by using Jones oxidation condition. So this is the chromium trioxide H2SO4 and acetone Jones oxidation condition, right? So this is a Jones oxidation condition to get this corresponding carboxylic acid. Now the next step is we are using 6 normal HCl. What it will do? So it will basically deprotect the mom group. Okay, and it will generate the corresponding our desired target molecule, right? So this is our target molecule. So we got our target molecule here. So just a minute. Okay, so coming to our next problem. So this is called monomorine. Okay, so this monomorine, it is an pheromone. Okay, so so it secretes from ant. Okay, it secretes from ant. Wait. So this monomorine, so this is an for pheromone, and it secretes from ant. Okay, and if you see the structure of this monomorine, so this monomorine, it is an bicyclic. It is fuse 6 5 fuse ring. So this 6 5 fuse ring, and in junction it is having nitrogen. And if you see this stereochemistry of hydrogen, it is beta. This methyl is alpha, and this side chain is having alpha. Okay, so three chiral centers are present in this molecule, and 6 5 ring junction. Okay, and ring junction is having nitrogen atom. So how we can plan for a retrosynthetic analysis? So we can plan from this one two three. So one the triketone. So this triketone we can plan via reductive amination. So basically we can plan for like ammonia, right? So this ammonia, if you have any question you can ask. Okay, sorry, just wait. Yeah, thank you. Just a minute. Just wait. I am unable to. Okay, my laptop is creating problem. Just a minute. I think I'll share it again. Okay, I will just leave now, and you can join after